Welcome back to the deep dive. Today we are plunging into a fascinating area of artificial intelligence that feels both incredibly powerful and, honestly, a little mysterious. Think about modern AI models, the ones that are now powering things like autonomous vehicles, navigating complex city streets, or systems that can sift through millions of images to find exactly what you're looking for. They're amazing, right? They can see and make decisions faster and often more accurately than humans in specific tasks.
Absolutely. And these aren't just simple pattern matchers anymore. We're talking about sophisticated object-level foundation models. Models like Grounding DINO or Florence-2. They're trained on absolutely massive amounts of data, learning incredibly rich concepts, and they have billions of parameters. They really represent a huge leap forward in capability.
But here's the big question, isn't it? How do they actually see? How do they decide that this group of pixels is a pedestrian crossing the road, or that blurry shape is the specific object you described in a text prompt? Maybe even more critically, when they get it wrong, when the self-driving car mistakes something or the image search fails, how in the world do we understand why? Because we need these systems to be reliable and trustworthy, especially when the stakes are high.
Precisely. That's the core problem. As these models become larger, more complex, and trained on diverse multimodal data, combining images and text, for example, they become less transparent. They start to feel like black boxes. This lack of transparency is a major challenge, especially, as you mentioned, in high-stakes applications like autonomous driving. Reliability and trustworthiness aren't just nice-to-haves there. They are absolutely paramount for safety. If we can't understand why a mistake happened, how can we prevent it from happening again?
So people have been trying to crack open these black boxes for a while, right? There are existing methods to try and understand what parts of an image an AI model focuses on, often called interpretable attribution methods. But the sources tell us these traditional methods really struggle with these newer, more complex foundation models. Why is that?
They do struggle, yeah. You can broadly categorize existing methods into two types. First, you have gradient-based methods. Think of tools like GradCam or maybe ODAM. These try to trace the decision back through the model using mathematical gradients, essentially seeing which parts of the input image most influenced the output score. The fundamental problem with these new multimodal foundation models is how they fuse visual and textual features deep inside. The gradient backpropagation gets influenced by both modalities. So that makes it incredibly hard to pinpoint exactly what visual parts were critical for the visual task alone.
Right, the signal gets muddled, by the text side of things.
Yeah, exactly. It reduces the effectiveness of attributing importance solely to the image input. It's just not clean.
Okay, so the internal complexity and multimodality trip up gradient methods. What about the second type?
Those are the perturbation-based methods, like DRISE. These methods try to understand importance by perturbing or removing parts of the input image and seeing how the model's output changes. If removing a region dramatically changes the decision, well, that region is deemed important. It's intuitive. But the issue here is that to get a good picture, you often have to try many different perturbations, which can introduce sampling artifacts or result in these kind of noisy saliency maps.
Saliency maps. Those are the visuals showing the hotspots of importance on the image.
Exactly. And the noise limits the fine-grained interpretability. You might get a general fuzzy area, but not the precise details of what visual elements mattered. The sources even describe maps from methods like DRISE as often being diffuse and lacked reliability, not very sharp.
So we have methods that are either confused by the internal structure or create noisy, imprecise maps. That leaves a real gap for accurately understanding these powerful new models. And that brings us to what we're diving into today.
Exactly. We're digging into a new approach proposed in an early 2024 paper by Ruoyu, Chen, and colleagues. It's called visual precision search, or VPS.
Visual precision search. Okay, that name already suggests they're aiming for something more focused and clear.
It does. And their mission with VPS, as stated in the sources, is really to offer a novel way to cut through this complexity and the limitations of prior methods. Their goal is pretty clear: generate accurate attribution maps with fewer regions and fundamentally bypass the internal model messiness that trips up gradient methods. They want to get a clearer, more precise picture of what specific visual inputs drive the model's decision on a specific object. And this isn't just another small tweak. It's presented as a significant academic innovation in how we approach explainable AI for these complex foundation models.
All right, let's unpack this innovation then. How does visual precision search actually achieve this precision and bypass the black box?
Well, that's the core idea and where the novelty really starts. VTS is explicitly designed to be gradient-free. It doesn't try to backpropagate through the complex, fused internal layers of the foundation model, which, as we just discussed, is where gradient methods run into trouble with multimodal inputs.
So it avoids that internal complexity altogether by working on the image itself.
Precisely. Instead, it's a search-based mechanism that operates directly on the input image. It treats the image as like a collection of visual parts, and it figures out which combination of those parts is the most important for the model's decision about a particular object. It's sort of like asking the model, given this image, what are the minimum visual clues you needed to see that object?
Okay, operating on the image directly to find the minimum essential clues. That makes sense. How does it actually do this search efficiently? Images are big.
Right. It starts with what they call sparse division. You can't just look at every single pixel or every possible blob of pixels. That would be computationally impossible, like you said. So the first step is to divide the input image into small, manageable sub-regions. They use a specific established algorithm for this called SIO superpixel segmentation. Think of this as automatically breaking the image down into visually coherent chunks, little parcels of pixels that kind of belong together based on color and texture. These superpixels become the basic units for the search.
Okay, so you got the image broken into these visually meaningful chunks, these superpixels. Then you need to figure out which subset of these chunks is the most important for the model's decision.
Right, exactly. And they frame this task as a subset selection problem. Now, on the surface, selecting the best subset of these regions sounds simple enough, but the sources point out that computationally, finding the absolute optimal subset by checking every single combination is a very hard problem, what computer scientists call NP-hard. It's practically impossible for any reasonable number of regions, just too many combinations.
Ah, okay. So this is where the academic core and the key innovation really come into play. How do they solve that impossible search problem efficiently?
Exactly. This is where they bring in a really powerful concept from mathematics and computer science called submodularity. Instead of exhaustively checking every subset, which is impossible, they designed a novel submodular function to score the importance of different sets of these subregions.
Submodular function. Okay, we need a simple way to grasp that academic concept. What does that mean for us?
Right, okay. Think of it like building a collection or gathering information. When you add the first few pieces to your collection, each new piece likely brings a lot of unique or novel value you didn't have before.
Look.
But as your collection grows, adding yet another piece might still be valuable, but the additional unique value it brings, the marginal gain beyond what you already have, might be less significant than what the first few pieces brought. This property, where the marginal gain from adding an element tends to decrease as your set grows, is called diminishing returns.
Okay, diminishing returns. Like adding different tools to a toolbox, the first few tools, maybe a hammer, a screwdriver, they add huge capability. But adding like a 10th or 11th specialized wrench might only be useful for very specific, less frequent tasks. It adds less new overall capability than the first tools did.
That's a great analogy. Perfect. So a function satisfying this diminishing returns property, along with being monotonic non-negative, meaning adding elements never decreases the score, is a submodular function. The crucial academic insight here, the real theoretical contribution, is that they were able to prove that their specific, novel scoring function for image regions is submodular. They proved it mathematically.
And why is proving that specific function is submodular so crucial for solving that NP-hard search problem? What does that unlock?
Because it provides strong theoretical grounding for efficiency, it means that even though finding the absolute optimal subset is NP-hard, if your scoring function is submodular, a simple greedy search algorithm can find an approximately optimal solution really efficiently. There are theoretical guarantees on how close that greedy solution is to the true optimum. This is the academic elegance of it. They frame the problem in a way that allows a powerful, proven optimization technique to be applied that lets them find a very good set of important regions without that impossible computation.
That's the powerful connection, using these deep theoretical properties to make a super hard problem tractable and guarantee a good outcome. Very clever. So what exactly goes into this novel submodular function? What specific aspects of image regions is it scoring to capture this idea of importance for the model?
This is another key innovation, how they actually defined the score, and it's tailored for object-level understanding. The function combines two main components, two key scores designed specifically for finding visual importance, the clue score and the collaboration score.
The clue score. Okay, that sounds like it's focused on regions that provide positive evidence, like clues in a detective story.
Exactly. The clue score focuses on identifying regions that help the model find the target object accurately and with high confidence, ideally using as few regions as possible. It measures how well a given set of subregions contributes to a high IOU that's intersection over union, the standard metric for how much a predicted bounding box overlaps with the true location and high confidence for the correct category. It's trying to find the regions that positively strengthen the desired positional and semantic response, as the paper puts it, finding the good stuff.
Okay, finding the regions that are strong, positive visual clues for the object. What about the collaboration score? That sounds different.
It is different, yeah. The collaboration score looks for regions that have strong combination effects. These are regions that might not be high scoring on their own, but are crucial when considered with others. More specifically, this score is high for regions whose removal from the full image causes the model's decision for the target object to fail significantly. Either the detection box just disappears, or its confidence or IOU drops dramatically. It's assessing the sensitivity of the decision to the absence of a region.
Okay. So clue is about finding regions that help when present, providing positive evidence. And collaboration is about finding regions that are so critical that their removal actually causes the decision to break down.
That's a great way to think about it. And the core academic innovation here is combining these two perspectives into that single submodular function. This combination allows VPS to identify regions that are both positively indicative, they provide clues, and critically sensitive, meaning their absence breaks the decision. It's not just about what makes the model succeed, but also understanding what makes it vulnerable and potentially fail.
That combination feels incredibly powerful for truly understanding the model's visual dependencies. It's capturing both sides of the coin, really.
It is. And once they have this novel submodular function that captures importance in this nuanced way, the greedy search algorithm takes over. It iteratively adds the subregion that provides the biggest marginal gain in the function's value at each step. This effectively ranks all the subregions from most to least important. The final attribution score for each subregion is determined by its marginal effect, essentially, how much the function value increased when that specific region was added to the growing set. These scores are then normalized to create the final saliency map.
So the academic innovation is in defining importance using these two complementary scores, the clue and collaboration scores, proving that this definition results in a submodular function, which then allows an efficient, theoretically backed search to find the most important visual regions.
Precisely. It's a theoretically grounded search on the input space that bypasses the internal complexities of the foundation model. It tackles the problem from the outside in, using some pretty clever design.
Okay, that makes a lot of sense from an academic and algorithmic perspective. Very neat. But why does this innovation matter in practice? Does it actually perform better than the old methods we talked about?
Absolutely. The experimental results presented in the paper are quite compelling, actually. They show that VPS offers superior performance, especially on these object-level foundation models. They evaluated VPS extensively on models like Grounding DINO and Florence-2 across different data sets covering general object detection, visual grounding, that's understanding text descriptions and images, and even detecting rare object classes.
Okay, how did it stack up against the baselines like DRISE or the gradient methods like ODAM?
It consistently outperformed them on key metrics. These are metrics designed to measure how faithful the explanation is to the model's actual behavior. They include metrics like insertion and deletion AUC scores, basically, how quickly performance changes as you add or remove the regions VPS identifies as important. Higher insertion and lower deletion are better, indicating the map correctly identifies regions that contribute to success or failure.
Give us some of the standout numbers or results. What kind of improvements are we talking about?
Okay, so looking at Grounding DINO, which is a well-known multimodal model, on a standard object detection task using the MS COCO dataset, VPS showed a significant improvement in how quickly the model finds the object as you add the VPS-identified regions. That's the insertion score. It showed over a 20% jump compared to DRISE. For visual grounding on RefCOCO, that insertion improvement was also substantial, around 20%. And notably, for the challenging task of detecting rare objects on the LVIS dataset, VPS showed an even larger gain in insertion, more than 30% better than DRISE. That indicates it's much better at identifying the crucial pixels for tricky cases.
Wow, okay. So it's better at finding the positive clues across different tasks. What about Florence-2? That's an LLM-based model, right? Different architecture.
Yeah, Florence-2 is interesting because it has a different architecture and doesn't output object confidence scores in quite the same way, which can be tricky for some explanation methods. Despite this, VPS still achieves state-of-the-art performance. For detection on MS COCO, it showed really impressive gains in the deletion metric. That's how quickly the detection fails when you remove the important regions. It showed a massive 50% improvement over DRISE. On RefCOCO for visual grounding, the dilution improvement was even larger, over 60%.
Huge numbers.
Yeah. This strongly validates the collaboration score component we talked about, and VPS's strength in identifying those critical dependencies whose removal causes failure. It works even in models lacking standard confidence outputs.
And visually, what do the saliency maps actually look like compared to the older methods? Are they clearer?
Oh yeah, the visuals are quite striking. Gradient methods often produce these diffuse, kind of blurry blobs. Perturbation methods can be noisy, like we said. Because VPS is selecting specific visual chunks, those superpixels, based on its precise scoring and search, it produces maps that sharply highlight essential subregions. They often align much better with actual object boundaries and class-specific visual cues. You get a much clearer picture of exactly what visual parts the model is focusing on. Much less ambiguous.
Okay, so it's quantifiably better on standard metrics,
Yeah.
and it provides visually sharper, more interpretable explanations. That's already great. But one of the most exciting potential applications you mentioned earlier was using this to understand failures. How does VPS provide novel insights into why the model gets things wrong? This seems really important.
This is a major contribution, I think. Providing a quantitative benchmark for understanding failure modes, which was really lacking before. Most failure analysis relied on just looking at examples, maybe anecdotally. VPS provides a data-driven, measurable way to understand the cause of the failure.
Okay, let's start with those visual grounding errors. When the model is asked to find an object based on text, but gets it wrong, maybe points to the wrong thing in the image.
Right. VPS is really good at identifying interference from other objects in the scene that confuse the model. So if you ask it to find the small blue chair, and there's several chairs or maybe other blue things around, VPS can highlight the distracting regions that pulled the model away from the correct target. Their analysis shows that for these visual grounding failure cases, the VPS map was much better at identifying the distracting elements than other methods, like a 43% improvement in insertion score over DRISE on those failure cases.
Wow, that's incredibly useful for debugging and improving models. What about standard object detection failures, like misclassification, when it sees something but calls it the wrong thing?
For misclassification, VPS reveals that often the background surrounding the object interferes with the model's decision-making. The saliency maps show importance kind of spreading into the background in these failure cases. This insight suggests a clear direction for model improvement. Maybe refining how models handle the contextual relationship between the foreground object and its surrounding environment. They introduced a metric called explaining successful rate, or ESR essentially, how often focusing on the VPS-identified regions helps clarify or sort of correct the failure. They saw significant ESR gains for misclassified cases, pointing directly to what went wrong visually.
So it shows the why behind the misclassification, suggesting that background context is confusing it. It gives a quantitative measure of how well that explanation works. That's powerful. What about objects that the model just misses entirely undetected objects?
VPS can also provide insights there too. Failures can arise from subtle visual cues, maybe occlusion or difficulty distinguishing similar objects. By highlighting the regions the model should have focused on but didn't, or highlighting confusing elements nearby, VPS reveals potential reasons for the misdetection. Again, they showed ESR gains for undetected cases, indicating the map helps in identifying why it was missed and potentially guiding a fix. It gives developers these concrete, data-driven clues about the model's blind spots.
It really sounds like VPS is not just showing where the model looks when it's right, but also giving us this rigorous, data-driven look at why it's wrong. That moves interpretation beyond just being a visualization tool to being a powerful debugging instrument.
Exactly. And they did tests, often called ablation studies, to validate their design choices, essentially, testing the components individually to see their impact. You want to make sure each piece is pulling its weight.
Right. What did those studies show about the clue and collaboration scores? Were they both necessary?
They confirmed the importance of both, yes. The clue score is very effective at finding regions that positively help detection and contribute to success, which leads to better insertion scores. It finds the good evidence. The collaboration score is critical for finding those sensitive regions, the ones whose removal breaks things. That enhances the deletion metric. It helps identify the parts whose removal causes the model to fail quickly. Combining both scores is essential and gives the best overall result across different metrics and failure types. You need both perspectives.
Okay, makes sense. And the initial step, dividing the image into subregions using superpixels. Does the number of regions matter? How fine-grained do you go?
Yes, it's a key factor, and it involves a trade-off. Their studies showed that generally, increasing the number of subregions leads to higher insertion and average highest scores, meaning finer divisions enhance the faithfulness of search results, both for correct and misclassified detections. The explanation becomes more granular and aligns better with subtle model behavior. However, there's a practical cost. Increasing the number of subregions rapidly increases inference time because the greedy search has many more elements to consider.
Right. So you can get a very detailed explanation, but it takes longer to compute. That makes sense. A classic trade-off. This visual precision search method seems like a significant step forward, especially with its theoretical backing and this ability to analyze failures quantitatively. But what are its current limitations, and where do they see this work going next?
Well, you touched on one limitation already, the computational cost. The greedy search, while efficient for submodular functions, can still be demanding if you use a very large number of subregions for maximum fidelity and detail.
Right, the time versus precision trade-off.
Another limitation they note is the quality of the initial sparse division into superpixels. If the superpixel algorithm itself isn't great for a particular image, if it incorrectly groups together regions that have opposite effects on the model's decision within a single subregion, well, that can potentially distort the attribution. The quality of that initial image breakdown matters.
Garbage in, garbage out, potentially.
Kind of, yeah. And you mentioned something about applicability to some models lacking confidence scores.
Right.
So while VPS worked well on Florence-2 in their tests, the strong theoretical guarantees for finding the approximately optimal solution are technically based on the assumption that the model can return relevant scores and candidate boxes for any combination of input subregions you show it. Some newer MLLM-based models may not directly output candidate boxes or confidence scores in the same way traditional detectors do. This might mean there's leaving room for improvement in the interpretation results for those specific different types of architectures where the guarantees don't perfectly hold.
Okay, so it's not a magic bullet for every possible model architecture yet, though it works very well for several important foundation models. What about future directions for this research? Where do they go from here?
They outline several exciting avenues. First, improving those initial sparse division strategies, perhaps making them adaptive or better suited for different types of images or scenarios to get more accurate subregions from the start, directly tackling that limitation. Second, making the search process faster, perhaps, by integrating external knowledge to pre-filter obviously unnecessary regions, or maybe exploring more efficient approximate search techniques beyond the standard greedy approach.
Okay, so directly addressing the limitations you just mentioned, computation and the initial division.
Exactly. Beyond that, they want to explore interpreting not just the input image, input level attribution, but also the internal parts or parameters of the model, especially for complex transformer-based architectures that are common in these models. That's a whole other level of explanation. Extending the method to other vision tasks beyond detection and grounding, like instant segmentation, is also a goal.
And perhaps the most intriguing direction, the one hinted at by the failure analysis.
Yes. Moving beyond XAI explanation AI purely for human understanding or debugging, they want to use these powerful explanations not just to understand the model, but to actively improve the models themselves. This could involve using the explanations to guide model training, maybe focusing more on regions where explanations show confusion, or automatically identifying and flagging strange or anomalous decisions during deployment by seeing if the explanation looks weird. Maybe even detecting potential hallucinations in multimodal models by seeing if the attribution makes sense relative to the input. Using the interpretation results to guide model training and enhance performance, or detect anomaly decisions by assessing whether the attribution distribution deviates from expected patterns.
Wow, that shifts the role of interpretation from just post hoc analysis to an active tool for building better, more reliable AI system.
Precisely. Using the insights gained from interpretation to directly inform and improve the system itself, making it a feedback loop for the AI.
So to wrap up this deep dive, visual precision search offers this really powerful, theoretically grounded new way to peer inside complex object-level foundation models like Grounding DINO and Florence-2. It moves past the limitations of older methods by being gradient-free and operating with precision on image subregions. Its core academic innovation lies in the clever design of that novel submodular function with its unique clue and collaboration scores, which captures a sophisticated definition of importance and allows an efficient, theoretically backed search.
Yeah, it's a significant step because it not only helps us understand why AI gets decisions right with improved fidelity and sharpness, but it also provides concrete, quantitative insights into why it fails. Whether that's interference from other objects, confusing background context, or difficulty with subtle features, this rigorous failure analysis is crucial for building more reliable and trustworthy AI systems, particularly in sensitive areas like autonomous driving, where understanding errors is absolutely paramount.
It really feels like a jump forward in making these complex models less of a black box and more understandable, more debuggable. And it leaves us with this thought to ponder, building on what we've learned today. If we can use AI interpretation methods like VPS to understand exactly why models fail or behave unexpectedly, could we eventually train AI models that are inherently more interpretable from the start? Or maybe even design systems that use these precise, failure-revealing explanations to automatically identify problems and improve their own performance without needing human analysis of every single error. Could the explanation itself become an automated feedback mechanism for the AI?
That's a fascinating possibility, isn't it? The explanations become part of the learning process itself, pushing AI towards self-improvement and perhaps inherent transparency.
Indeed. Something truly exciting to think about for the future of AI. Thanks for guiding us through this complex but really crucial topic.
My pleasure. It was great discussing it.